Counting matter. Learning about counting matter. Molecular mass and mole concept. When elements or compounds react with one another, it becomes necessary to know how many molecules or atoms are taking part in the chemical reaction. For this, a new concept of mole was introduced. What is mole? 1 mole of a substance is equal to its atomic mass or molecular mass expressed in terms of grams. Example, the molecular mass of oxygen is 32. 1 molecule of oxygen contains 2 atoms and the mass of each atom is 16. 32 grams of oxygen is equal to 1 mole of oxygen. One of the most well-known scientists, Avogadro, experimentally found that 1 mole of any atom or molecule always contains 6.022 into 10 raised to power 23 atoms or molecules. This number is called the Avogadro number, denoted by N0. Avogadro defined a mole as a collection of 6.022 into 10 raised to power 23 number of atoms or molecules. Just as in daily life, we use the words like dozen, 12, century, 100, cross, 144, etc. Example, how many molecules are present in 42 gram of nitrogen? Atomic mass of nitrogen is 14. Solution. Nitrogen is a diatomic molecule. Thus, the molecular mass of nitrogen is 2 into 14 is equal to 28. The number of molecules of nitrogen is equal to molecular mass of nitrogen is equal to 42 upon 28, that is 1.5 moles. 1 mole contains 6.022 into 10 raised to the power 23 molecules. Therefore, 1.5 moles will contain 15 into 6.022 into 10 raised to the power 23 molecules. Mole of oxygen molecule. 6.022 into 10 raised to the power 23 number of particles, that is 32 gram of oxygen. Atoms or molecules or ions. When molecular mass is expressed in grams, it is called as gram molecular mass. Similarly, when atomic mass is expressed in grams, it is called as gram atomic mass or gram atom. Valency. The combining capacity of an element is known as its valency. The electrons in the outermost orbit of an atom of an element are called valence electrons. The number of electrons denoted or accepted in order to form an octet in the outermost orbit of an atom of an element. Let us take examples. The electronic configuration of sodium Na is 2, 8, 1. It has 1 electron in its third orbit. Sodium tends to give up this electron so that it is left with a state 2, 8, which is stable. The loss of 1 electron leads to the formation of sodium ion, that is Na+, which is positively charged as it has lost 1 electron. Therefore, the valency of Na is 1. The electronic configuration of chlorine, that is Cl, is 2, 8, 7. It needs 1 electron in its third orbit to complete its octet and become stable. When Na and Cl atoms come together, Na gives up 1 electron to Cl. It takes up this electron and changes into chloride ion, that is Cl-. 2, 8, 8. The valency of Cl is 1. A+ and Cl- are bounded to each other by this transfer and form a compound sodium chloride, that is NaCl, which is the chemical name for common salt, an integral part of our food. The electronic configuration of nitrogen, that is N, is 2, 5. It needs 3 electrons to complete its octet. It completes its octet by sharing 1 electron each with 3 hydrogen atoms whose electronic configuration is 1 to form the compound ammonia, NH3, which is a stronger smelling gas. The valency of nitrogen is 3 and that of hydrogen is 1. Hydrogen is an exception to the rule. It has only 1 valence electron. Hence, it shows a tendency to either give it electron or share it. Therefore, its valency is 1. The elements having atom with full electron shells, that is helium, neon, argon, are chemically inert. These atoms are stable because they do not tend to give, accept, or share electrons. What are the valencies of the elements given below? Valency of the elements: carbon 4, magnesium 2, oxygen 2. Sometimes groups of atoms also give up or accept electrons, forming positive or negative groups. Such atoms or group of atoms having a positive or negative charge are known as radicals. Sometimes positive or negative sign is written before their valency to indicate whether they denote or accept electrons. Electrons, which any atom denotes or accepts, is also indicated through symbols. For example, sodium ion is written as Na+, and chloride ion is written as Cl-. Magnesium ion is written as Mg2+, indicating that the valency of Mg is +2 and that it tends to denote 2 electrons while forming a compound. Following is the list of some commonly used ions and radicals. Knowledge of ions and radicals is useful in writing molecular formula of a compound, as well as to understand and to write balanced chemical equations. Ions and radicals. Some elements show variable valency. The alternate valency shown by elements is indicated in bracket by the side of the ions in Roman figures. Chemical formulae of compounds. Let us use the above table to write formulae of some common compounds. Potassium chloride. Write the symbols of potassium and chlorine. The symbol of potassium is K and the symbol of chlorine is Cl. Write the valencies below the symbols. The symbol of potassium is K and its valency is +1. The symbol of chlorine is Cl and its valency is -1. Cross multiply the valencies. The formula of potassium chloride is KCl. Formula of water. Write the valencies below the symbols. H. Its valency is +1. O. Its valency is -2. Now, cross multiply the valencies. The formula of water is H2O. Formula of sodium sulfate NaSO4. Sodium +1 and sulfate -2. cross-multiply the valencies. Formula of sodium sulfate, that is Na2SO4. In the above examples, the charges on the ions have been balanced. Write the formulae of the following compounds using the table of valencies. Magnesium chloride, silver nitrate, potassium hydroxide, ammonium sulfate. Given valencies, Mg is equal to 2, Ag is equal to 1, K is equal to 1, NH4 is equal to 1, NO3 is equal to 1, SO4 is equal to 2, OH is equal to 1, magnesium chloride is equal to MgCl2. Note: this formula is obtained as follows. Symbols of magnesium, that is Mg, and chlorine, that is Cl. The valencies below the symbols. The symbol of magnesium is Mg and its valency is +2, and that of the symbol of chlorine is Cl and its valency is -1. Cross-multiply the valencies. So, the formula for magnesium chloride is MgCl2. Silver nitrate is equal to EgNO3. Note: this formula is obtained as follows. Symbols of silver, that is Ag, and nitrate is NO3. The valencies below the symbols. The symbol of silver is Ag, and its valency is +1. The symbol of nitrate is NO3, and its valency is -1. Cross-multiply the valencies. The formula of silver nitrate is AgNO3. Potassium hydroxide is equal to KOH. Note: this formula is obtained as follows. The symbols of potassium is K and hydroxide is OH. The valencies below the symbols. The symbol of potassium is K and its valency is +1. The symbol of hydroxide is OH and its valency is -1. Cross-multiply the valencies. The formula of potassium hydroxide is KOH. Ammonium sulfate is equal to NH4 is base 2, SO4. This formula is obtained as follows. The symbols of ammonium is NH4 is base 2 and sulfate is SO4. The valencies below the symbols. The symbol of ammonia is NH4 and its valency is +1. The symbol of sulfate is SO4 and its valency is -2. Cross-multiply the valencies. So, the formula of ammonium sulfate is NH4 is base 2, SO4. Summary: a mole of a substance is equal to its atomic mass or molecular mass expressed in terms of grams. Avogadro defined a mole as a collection of 6.022 into 10 raised to the power 23 number of atoms or molecules. Just as in daily life we use the words like dozen, that is 12, century, 100, cross, 144, etc. When molecular mass is expressed in grams, it is called as gram molecular mass. When atomic mass is expressed in grams, it is called as gram atomic mass or gram atom. The combining capacity of an element is known as its valency. The electrons in the outermost orbit of an atom of an element are called valence electrons. So, that is all in this topic, students. Learning is fun, so keep learning.